Physics seems easy. There are equations that determine the behavior of the microscopic constituents of nature, such as electrons, quarks, and gluons that make up atoms. For individual particles, it is called the Dirac equation, and it has very simple solutions. In our day-to-day life, however, we don't care about individual electrons. We always deal with big, tangible pieces of material. This cup contains a liquid, the tea, a metal, the spoon, while the cup itself is made of porcelain. All of these materials have macroscopic properties. For instance, metal conducts electricity. Porcelain does not. The tea flows, while the spoon and cup do not. How do we predict and understand these important properties, and others like them, starting from what we know about individual particles? Every big piece of matter is, after all, a collection of molecules, themselves made of atoms, themselves made of electrons, etc. In other words, nothing but a pile of elementary particles. And this is true of the spoon, the tea in the cup itself, and also you. We could try to solve our equation for all the particles involved. How many? Well, in our cup of tea, there are almost 10 to the 26 of them in concert, all interacting with one another in complicated ways. The problem is so complex that we simply cannot solve it. And somewhere in this complexity lies the key to understanding why the cup doesn't flow and the tea does. We call this emergence. The macroscopic properties like conductivity and fluidity are not fundamental. They have nothing to do with the constituents. Instead, they emerge from the collective behavior of a large number of them. The Nobel Prize winner Philip Anderson referred to emergence as more is different. In some materials, the interactions between the microscopic particles are very strong. In these cases, emergent phenomena are especially fascinating, surprising, but even harder to understand. Impossible? Some such systems show a very exotic form of emergence. What emerges is not normal matter, but something completely different, a theory of gravity, and, as if it were not enough, one that lives in one dimension higher. This is great because we know a lot about gravity via Einstein's theory of general relativity, and we can now use it also to study materials and systems that were thought too complex to be understood. This is called holography because, like holograms, it relates objects in different dimensions. The challenge of this approach is to find strongly interacting materials that share enough of their features with systems that have holographic emergence. A celebrated example concerns a highly exotic material, the quantum liquid formed in the collision of two heavy nuclei like gold, the quark-gluon liquid. This material is of relevance in the early stages of the evolution of our universe and is currently studied in laboratories in Brookhaven as well as CERN in Geneva. This material forms a strongly interacting quantum liquid whose properties are extremely hard to compute. However, in the early 2000s, a group of theoretical physicists used holography to calculate one of the liquid's properties, its viscosity. They understood that a system they were familiar with, called supersymmetric Yang-Mills theory in 3 space dimensions, was close to the real quark-gluon liquid. And in fact, the value of the viscosity they calculated using holography is strikingly close to the one measured in experiment. Holography has since provided an inspiring tool to study systems such as strongly correlated electron materials, the quark-gluon plasma, or high-temperature superconductors. Holography might allow us to understand the most exotic states of matter we know of.